Hey everyone, thanks for joining us today. So today we're going to be talking about real-time vector search for Amazon MemoryDB. We'll give you a quick overview of MemoryDB and the vector search capabilities enabled on it. And then finally, I'm joined here today by Ram Natarajan, who's joining us from Fidelity in India. He's a VP of Data Architecture, and he'll walk us through their use cases and their decision matrix to choose MemoryDB as a vector store. So one quote I want to read to you really quickly is this great quote from Swami. Everyone has access to the same models, so data is what distinguishes generic AI from generative AI that understands the business and the customers. The key point to really take away here is that your proprietary data is really what differentiates your generative AI applications. And vector search really enables you to actually take advantage of that proprietary data and feed that into your LLMs or your generative AI applications. So to give you a quick overview of MemoryDB. So MemoryDB is AWS's fastest database. It's fully managed, it's durable through a multi-AZ transaction log, and it provides 4 nines of durability. We also prioritize open source compatibility, and it's compatible with Redis OSS and also Valkey. So what is Valkey, if many of you aren't familiar? So Redis in March changed their open source licensing, and Valkey was a fork generated by the Linux Foundation that has a permissible open source license, and it's also a drop-in replacement for Redis OSS 7.2. There's 40 plus organizations and over 1 million container pulls. So what we've done is really enabled vector search for MemoryDB on both the Valkey and the Redis OSS engines. So MemoryDB, as I noted, is the fastest vector search offering on AWS amongst popular vector databases at the highest levels of recall. Many customers trust MemoryDB for their generative AI applications. It allows you to store millions of vectors and provide P99 single-digit millisecond vector search queries and updates and various CRUD operations. And we're also integrated into LangChain, so you can use our in-memory driver to quickly spin up your applications. And lastly, vector search for MemoryDB obviously enables many different use cases. It enables fast semantic search, such as Amazon Ads, using it to serve ads to you on Amazon.com. It provides durable semantic caching capabilities to really cache off prior LLM inferences, such that in subsequent semantically similar questions, you can actually serve the answer from the vector store without hitting the LLM again and incurring that performance and cost. And then additionally, retrieval augmented generation. So really using your proprietary data to provide context to your LLMs to provide a more specific answer to your users. And then finally, anomaly detection. So really detecting fraudulent behavior within single-digit millisecond latencies. So with that, I'm going to hand it off to Ram, who will actually step us through their Fidelity's use cases and their decision matrix and how they decided on using MemoryDB as a vector store. So I'll hand it off to Ram.
Thank you. Thank you, Sanjit, for that excellent context setting. So I'm Ram, working as an architect with about 20 plus years of experience and specialized in the intersection of AI and data. So have been with Fidelity for about 10 plus years, and our company is in the business of providing financial independence to our end customers. So today I'm excited to share our journey towards discovering the immense potential of vector databases. And our exploration was primarily driven by certain precise use cases which we found we couldn't effectively address using conventional databases. So with that in context, I would like to share one of the use cases that we have with financial markets. So we have market participants, that is analyst and a trader. So analyst would be more focused on historical data, and he would be doing more of fundamental analysis comprising of economic data. On the other hand, a trader is more interested and engaged in the act of trading and interested in the current data, which is more towards the latest earning data. So we know their roles are different. So let's look at a high-level design how this could be solution. So you would have the unstructured data coming in, which could be the research notes typed in by the analyst, or it could be the SEC filings, which is coming in like the 10K filings, and the data which is pertaining to the earnings data. So all of these are PDF documents. What we do is we apply an appropriate chunking strategy depending upon your business use case. And once it is chunked, once it is converted into meaningful sentences, what we do is we run it through an embedding model, and that embedding model would generate vectors. So when you think of a vector with 768 dimensions, all you can imagine it as an array of numbers, array of comma-separated values, and you can assume the length of that array is about 768. So this is on pure computer engineering terms. So these vectors get persistently stored into a vector database, and what we do is, while we push this data into the vector database, we also do the metadata extraction. So this would be the company name, the stock symbol, and it could also be more of metadata like what is the report date, what is the report name. So these metadata gets flowed into the vector database and it's stored alongside the vectors. So we index both the vectors as well as the metadata for the faster search. So going back to our use case, right? We spoke about having information barriers between the analyst and the traders. And we also need to make sure that users with appropriate entitlements are only able to access the data. So it's very clear that we have to embed in vector search a capability for role-based access control. So with that in context, let's go to the next use case. So our next use case is on self-help incident management. So I think most of us would be familiar with this. So this empowers individuals to perform technical or arrive at solutions for their technical issues. And how is it done? It is done by leveraging a pre-built knowledge base. And why is it done? It's because you can reduce the dependency on your IT support and also accelerate the ID resolution, problem resolution. So quick look at how the design looks, right? So you would have incident descriptions, you will have service request descriptions, and what we do is we kind of take those descriptions and resolutions, arrive at chunking strategy, which is packaging them into meaningful sentences. And what we do is we run these chunks through an embedding model. And these embedding models will generate vectors like previous case, and it gets persistently stored in a vector database. And what we also do is you would have some amount of metadata that is carried upon, and these metadata would be pertaining to the incident severity. It could be pertaining to the category of the incident, whether it is a batch of failure or a data management. And these vectors get into the vector database, metadata, and the vectors get indexed for faster search. Let's assume a user is coming in and typing a question which is server is unreachable, and we are getting a timeout error. So what happens is, while the user fills this in the web UI, he would be giving good amount of metadata, like the category is on servers and storage, the application is going to be a data warehousing application, and the assignment group is going to be Unix engineering. So let's say we have built a vector database with about 5,000 IM tickets. You're going to query a finite set of them, which is about like 500 of them, and this is going to filter out and arrive at a finite set. And what we are going to do is the incoming English-like query, which the user is typing, gets converted into a vector, and we go and find out a matching vector in these 500 finite set and arrive at the top 3 matches. And this could be used either for downstream search use cases, or probably it could be fed into an LLM. So we can go on, but at a broader pattern, what we found holistically is cutting across various business units, what we found was there are concurrent users who want to perform a low latency search. And while they do that, they want to make sure that the role-based access control is implemented. and it's very highly unlikely that they're doing a pure play vector search. There is always some sort of metadata associated with it, and these metadata could be with something related to a text attribute, which is like a product, 401k, or a student debt, or it could be a numeric filter, which could be account balance greater than 10,000 or something of that sort. So this was the requirement broadly from the data scientists, but there were requirements from the data engineers too, right? So the ML engineers, what they had in mind is the vector database has to be co-located with the models. And we all know that AI is going to be in cloud. So one of the requirements that we got as architects is make sure that the vector store is portable. And the reason they ask for it is, one is to have better resiliency patterns so that you're not building cross-cloud dependencies. And the second thing is the ingress and egress which goes inside the cloud, right? So that being said, the final one what we got was on the velocity, which is faster time to production. Teams want to reduce their effort on sysops and get more into, put their effort more into looking into business requirements. So that is something where they were looking for a managed service. So we looked into the use cases, we looked into the patterns. So capability metrics, right? So at Fidelity, what we do is, before getting into the choice of tool or before getting into the solution, we build a capability matrix which keeps us very fungible. So we can port it to another vector database or probably into another cloud. So we build a capability matrix. So let's see how that looks, right? So on the data storage, which is a functional requirement, you would have three main capabilities. One, a capability for storing vector data types. Second, indexing the vectors. The third, performing CRUD operations on the vector, which would be create, update, and delete, not just on the persistent storage, but also in memory at cache level. On the consumption, broadly, we all know there is two. One is batch, another one is real time. That is the way we consume. But while we do that, do we have enough APIs so that we could invoke it from SageMaker or invoke it from frameworks like LangChain, Llama Index? On the data processing, if you look at it, we do vector operations, which would be like additions, subtractions, or we would be trying to find the closest vectors using Euclidean distance or cosine distance. But while we do this, what we had in mind is how much we could parallelize, what is the number of concurrency that we could achieve. Moving on into data security, Sanjit already touched upon in the MemoryDB capabilities. So one of them, what we found was encryption at rest and encryption at transit. The second thing is role-based access control, which we spoke about. Third thing is, are we having our data in a single tenanted instance, or is it going to be multi-tenanted? Within our VPC just dedicated to Fidelity, or is it going to be shared across multiple tenants? So looking into the non-functional requirements, so the first thing is on cloud operations, right? So the thing that we have in mind is multi-cloud, which we started off, and the second main thing which we found is on monitoring and alerting. So when we start building a vector database, we don't want to be building the peripherals around the vector database, which could be something related to monitoring the CPU, monitoring the memory, network, number of concurrent users, authentication. So should we be building all these, or is there a vector database managed service which could give us all these monitoring and alerting out of the box? So on metrics and KPI, let's keep it simple. So once we decide the application tier rating, we want to be very clear on the SLA and SLO adherence. So that is about the metrics and KPI. Non-functional, you have a lot of them, but let's focus on operations and support. So how much of an effort it would be if we want to upgrade from version 7.1 to 7.2, right? How much of an effort that our infrastructure teams has to put into. The second thing is, let's say the application footprint is increasing. How are we going to do, or how much of a heavy lift it is going to be when we want to go from a 4x large to an 8x large? So these are the things that we had in mind when we built the vector databases. So moving on from the tech and architecture, so nothing is complete without the architecture, justifying my presence here. So we looked into the use cases, we looked into the patterns, we arrived at a capability matrix. Let's see whether architecture has a unique view on this. So one of the things what we had in mind is when we chose the indexing, we want to be very clear that we don't want to buy into custom indexing. We want to go for an index which has good amount of industry literature. Anybody can go and it is flexible and configurable, and we want to make sure that it's very highly available. Reason for that is, let's say we shift to another vector database or we go to another cloud, we have good amount of literature available on the net to go through and configure the index. So another thing to mention about is the non-lossy compression, right? So when you take a vector, we saw it as comma separated values. So let's say the floating point values are 32. We can do a compaction and bring it down to floating point 16. So what it would do is, it would reduce our storage footprint. But what we lose on the process is we are losing the accuracy. So what we want to do is we want to go for some sort of a non-lossy compression wherein we don't lose the accuracy, but at the same time our storage footprint is less. And looking into data integration or data ingestion, so what we found was there are multiple utilities and libraries which these ML frameworks provides to ingest vectors into the vector database. But what we found primary was, does the vector database provide something out of the box to ingest vectors parallelly? So that was on the data ingestion. Out of the box observability, and we spoke about the monitoring and observability. There are about 42 metrics which we found in MemoryDB for Redis out of the box. And on the scaling we already spoke about, right? Vertical scaling and how do we do upgrades and all of that. So I would like to take a quick pass, right? So when we do the performance benchmarking, what we assumed in mind is, let's say all of us in this room are given 3 vectors, A, B, and C, and we are asked to find the closest vectors using cosine distance. All of us would arrive at the same result because it's pure play mathematics, right? So that's what we had in mind. So what we did was we took an industry data set where the ground truth is known, and we evaluated across various vector database that is available. And what we found is, these are the results that is displayed on the screen for Amazon MemoryDB for Redis. We found that we were able to get to a 99% recall. And we were able to do that in less than 25 milliseconds latency. And there are about 790 concurrent users looking at it. So what we heard as a requirement is, we are okay with 97% recall, but is there a way we could bring the latency to single digit? So we were able to get to single digit latency by compromising a little bit on recall. So net, we were able to balance the speed and quality. And the second thing we spoke about was the non-lossy compression. So on non-lossy compression, what we found was, there is a very specific data type which is hash data type in MemoryDB for Redis. What it helps us to do is, the storage footprint is about 1/4 of the original one, but what we get is the same accuracy and same recall. So how did we arrive at a decision of choosing this for our use cases, right? So we want to give a quick summary. 3 things which we had in mind, right? So one of them is when we did the sizing calculator, we put in the vectors, we put in the dimensions, it came out with a recommended instance, which is very handy, and data is within the Fidelity's VPC, and we were also able to back up that using a very specific RDB format, and this allows us to restore it in other clouds or probably into Azure. And then there is also a secure token-based authentication. So you have user ID and password-based authentication. So what we found was industry is moving away from it, so we were able to get into more of a token-based authentication. So we hope we have reached a safe harbor in our decisioning, and we want to say how the tech objectives is driving the business outcomes, right? So one of them, what we spoke about, is information barriers between the analysts and the traders. So we were able to define a key space, and we were able to say that funda : star, right? When we create a user in Redis, we create a user with this access string, so it restricts the access to that particular analyst user, so that traders are not able to access that. On the other one, we also found about metadata filters on querying the incident management. We were able to use servers and storage as a filter and get to a very finite set. So our use cases are brought to life, and these are the implementation. With this, thanks to AWS for hosting us tonight, and thanks to Fidelity India for flying me here, and I'm really honored to present before this learned and practicing audiences. I would like to hand it over to Sanjit for the closing note.
So thanks everyone for joining. Here are some great links at GitHub with some of these MemoryDB APIs to spin up your own kind of vector search capabilities, a semantic caching blog, and also our in-memory driver with LangChain to kind of build up your generative AI applications. So thank you everyone. Please fill out the survey. We really appreciate your feedback. So thank you.